This is the load profile. It's a way of approximating the energy consumption, the daily energy consumption of a building or of any other system, basically. And it's based on the fact that you just simply take the input power of the appliances and multiply it by their runtime per day, which results in an energy consumption, and it's also divided by 1,000 to produce kilowatt hours per day. The thing to look for here is that you're basically trying to assemble the most energy demanding day of year. However, it's nice to keep in mind that not every day is going to be like this. And so that's why it's just roughly approximation. If you were to be more exact, you would have to model it for a weekly schedule, for which you could set up well, a bigger Excel sheet, or you could actually use modeling software, but I don't know if there's any modeling software that is available for free. So if you're just doing it on your own, this is pretty much as far as you can get. If not, I would like to know. But what's nice to keep in mind that apart from all the appliances, there are going to be things like servers and other things that actually consume some amount of energy per day. So it's nice to keep that in mind. Also, if you use a sauna for, in this case, there is a infrasauna installed, which usually runs for 1 hour. Well, not every day, but let's have that here. The refrigerator is kind of just an approximation. The actual consumption is probably going to be less because it doesn't run on 200 watts all the day. It doesn't run at full power all the day. That's just about it. But you know, just to have it here, it's really nice. Now I will show you where I got this value for the heat pump, and I will also mention that it's nice to have in mind some room for EV charging if you're planning to drive EV or have one, and how to simply calculate that. So this leaves us with 74 kilowatt hours a day, which is a huge ton of energy, actually. And so how do we design the battery capacity for the autonomous thing? Now, there's a formula that basically takes into account the number of autonomous days, and now this could either be the requirement of the investor, or it could be based on climate data analysis. Pretty much you're gonna want to look into like winter months, well, at least in this climate, where there's the least amount of sunshine and the highest energy consumption, which is probably going to be somewhere between like December, January, February, things like that. And so you need to really look into the data. Then it takes into account the depth of discharge, and this is a battery specific value. There is 0.8, however, some batteries might have a more positive value. However, you really want to use it only if the manufacturer states a higher value. And then, of course, the system voltage. There might be a 60 volt system, so for a series of 4 12 volt batteries, am I correct? 12, 24, 36, 45. Okay, 5 12 volt batteries, a total 60 volt. And so that leaves us with the battery capacity of 7,500 amp hours with the 60 volt batteries. That's quite a lot. And in kilowatt hours, for just for reference, it's 450. Now, we can have a look at what the 450 kilowatt hour battery would actually look like or cost. Now, I am doubtful of whether the investor is going to want to invest in that. And the question is actually, would the system run autonomously, even provided that we set up the load profile? Well, there are some other things to take into consideration. So I'm gonna leave you with this for now, and we might dive into the data later. Note of how I got the 1157 kilowatt hour value for the EV. So provided that you're going to be driving something like a Tesla Model Y, which could be a family car of the EV species, we're going to have a look at the battery capacity, which is for the performance model 81 kilowatt hours. And you're probably not going to drive the whole tank every day. So let's say that you drive 1/7 of the range per day, which should be enough for you to get to work and back or wherever you need to. And so it's just 81 divided by 7. That's a daily value you could use for the load profile in this case. The Excel sheet of the heat pump data consumption, it's logged from 24 to 25. So we've pretty much got 1 year of data here. And it logs the hourly data, at least for some period of time, daily data and monthly data for the complete year of 24. So this is the data that I used for the energy consumption because it's, well, monthly. And so what we get actually logged here is the output produced total, environment, heater, compressor, outer temperature, room temperature, and hot water temperature. And now, so which of these four values are interesting to us? Well, it's the first one, because although this value is higher, it's actually based on the concept of the heat pump. And so by dividing those two values, you could get the COP value, the actually experimentally measured COP value for each month here. And so the heat pump actually produces more heat than it consumes electricity, because it basically produces energy from the air temperature potential on the outside of the building. And so therefore we're about the output produced total, which is indeed actually the input, the power input. Now for the load profile, I just checked here and looked for the highest daily value, which was here 37.1 kilowatt hours, which occurred on the 14th of December last year. You might actually go a little bit deeper and ask yourself, like, how many consecutive days are here with this value? Well, no, it was the peak value. So you might maybe take like 5 days or a week into consideration. And then if you were to run a weekly load profile, you would kind of get a sum of a week. And I would base this week on the actual, either the outside temperature, where you'd look for the lowest value, or the lowest value of sunshine. Or we're gonna have a look at snow data a little later. So in this location, there's actually quite high potential for snow coverage in winter. And so you want to be safe actually by assuring that the panels are not going to be covered in snow. We're going to see what the data says. However, it's also not very precise to base it just on that data, because, well, the amount of newly fallen snow doesn't always mean it sticks to a slanted roof or a gable roof. But at the same time, I have seen actually autonomous houses where they pretty much, because of snow, need to clean the panels with like a telescopic brow, which is a way of doing things if you're planning to be fully autonomous. So just keep that in mind, that in areas where there is snow potential, you might consider that. Ask PV to plot is monthly data, and in this case it reaches back to 2005. Now, as a part or as opposed to the daily data, this is actually the energy production in kilowatt hours per square meter per given month. And you can see pretty clearly that you can make averages out of this, but pretty much in every year, let's say 2020, the production is lowest in, here it's December. January goes for 33 kilowatt hours per square meter month. A little bit higher is February, and then the peak values are going to be May. Here, that's interesting. Okay, July is even higher. So July probably. If you look at 2019, you can get pretty similar results with June being the highest here, and the lowest being probably December with 83 kilowatt hours per month. And if you're planning to work with this data later, there's a trick for numbers, or works in Excel, that allows you to actually find and replace all of those dots and replace them with commas, because the numbers don't like really working with these. So just press Command F, find the dots and replace them with commas. As you can see, replaces all of them in one click. Now, the thing you can ask PV to plot is daily data for your plane, so with a specified slope and azimuth. Now, what this plots is actually an average day for a selected month, so in this case January, and we can see that an average day in January is gonna produce, well, this is not the energy production, that's important to notice. This is actually the sun irradiation at specified time, and so the peak is gonna be probably about 11 a.m., 12 a.m., something like that, with the value here being 221 watt per square meter. Now, it's important also to dissect what these values mean. And so what's more important for us is the global irradiance, which is actually or should be approximately a sum of the direct irradiance and diffuse irradiance. The other values, which are even higher, are the global irradiance on a 2-axis tracking plane. So this is in case you install a PV system, usually not on a gable roof, but maybe in other types of systems, which actually moves accordingly to where the sun is at a specified time. And so this can maximize the power output, which is really nice, but you need to have a kind of a structure, and it needs some amount of power to be able to actually steer the panel to the right direction. Not our case, just wanted to mention that. So the direct irradiance is, well, pretty obvious. It's the irradiance that faces directly the plane, and the diffuse irradiance, what it means is actually irradiance that is reflected from other surfaces to the panel. And so we're going to use the global irradiance, which is the total value. So as I was talking about the snow data, here we've got data available from the year 61, which is a lot of data. And so this is a month-day value, and you could actually go through the whole sheet and look for the data, or you could set up a macro that would look it up for you, but I'm just gonna go through the last couple of years. And so what we're looking for is actually consecutive days with new snow. And so here we can see December 23, there are 2 days. And I don't think we're gonna find a much higher value than 3 actually. So 22, let's go over to, there are 2, maybe 3 days here in November 21. And that's probably about it. If you're gonna go a little further, you might find probably another 3 days. If you look more further into the past, probably you'll find a greater value, but it's also due to the fact that, from my own experience, the amount of newly fallen snow is decreasing. Interesting, 2018, 2, 3, 4, 5, 6 days of consecutive snow. So now you could use this value for the number of autonomous days. However, it's not that serious. Here you get like 1 centimeter of snow, and as I said, it's not a given fact that the snow will actually stay on the roof and stick. So this is just something additional that you might take into consideration when coming up with the value for the number of autonomous days. Nice. So you might be asking, if we now fulfilled the first condition, well, if we would fulfill the first condition, which is the monthly production being higher than the consumption every single month, that's great. The second condition being the battery capacity being sufficient for a number of autonomous days. Well, the question arises, is that enough to say the system can run fully autonomously? And the answer is kind of complicated, but I would say we would definitely need to have a look at more precise hourly at best data, especially in the months of January, December, February, and really determine whether we can actually produce the energy within, let's say, a given week, for which we would also need a more precise load profile. Would you be interested in going through more precise data? Let me know in the comments. I am curious about what you have to say about the project or about anything else. There is one thing you might be asking yourself, and that is why I do not have studio lights yet, and I do not know how to answer that question. However, yes, the background is very shady. So I'm looking forward to seeing you in the next video. Till then, take care. Ciao.